Excellent. Good evening and welcome to Cook the Science. It's a pleasure to have you here tonight. My name is Thomas Michaels. I'm a professor of soft and living matter physics here at ETH Zurich in the Department of Biology, where I'm also a member of the Bringing Materials to Life Consortium and also of the World Food System Center here at ETH. It's really lovely to see so many of you, a packed room. It's really amazing. And tonight is even a special event. So it's a slightly special edition of Cook the Science because we are part of the ETH Food Day, which has been organized today. And this is a really wonderful opportunity for us because we are part of this World Food Systems Center that has organized this event today. And the World Food Systems Center is an amazing initiative here at ETH that tries to bring together different people, actually over 50 research groups across over 8 departments at ETH, and provides a wonderful platform and competence center both for research, education, and also for outreach. And this is why we are here tonight. Now, for the people that are new to Cook the Science is a public lecture series that we organize here at ETH, where we try to bring science closer to the public using something that we all love, which is cooking. And cooking provides such a nice platform to explain very fascinating scientific concepts in a way that is very relatable. And every evening, we try to cover a different science kitchen topic. And we try to do this with the help of scientists and chefs. So we really look also at the cooking perspective. And the topic tonight is related with the ETH Food Day. It's about plant-based cooking. And in particular, we will focus a lot about tofu and how we can change the texture and transform it into something really delicious. So we will learn a lot of very fascinating techniques. And to tell us a little bit about this fascinating world of plant-based cooking, in particular tofu, we have two wonderful guests tonight. On the science side, we have Professor Patrick Rühs, and our chef tonight is Michaela Frank. So Patrick, before joining ETH, was head of science at Fermented, which, if you probably know, if you've been to Migros or Coop, it's a plant-based product. And is now professor here at ETH, where really with his work, with his group, he works really on how processing changes the structure of food. So it's a really relevant topic tonight. And Michaela is a wonderful chef. She was a head chef at Rank, where she became the Zurich youngest chef with 14 points in the guide Gold Milo. So wonderful achievement. And she's now done 1 year as a solo, wandering around Switzerland and the world, presenting her kitchen and cooking prelibacies really around the world. And she works a lot with plant-based foods, and those in particular with tofu, as we will see tonight. So you're really the perfect person to teach us from the cooking side. So this is a really wonderful evening, I think. The topic is fantastic from the science perspective. We have a lot to cover, so I think let's get started. And the floor is yours, Michaela.
Thank you so much. Welcome, everyone. I quickly give an introduction about myself. So I'm Michaela, and I was a head chef. And after being a head chef for quite a long time with a lot of adventures, I chose to quit and do my own stuff without any boundaries. And I do a lot of work with pop-ups or with brands or anything, but one brand maybe is very fitting for tonight is the Swiss Legume Association. I very proudly was given the opportunity to actually create some dinners with them and also some recipes for them. And just recently, like 1 month ago, I got to cook for the Swiss Embassy in China for a 1 month long project to celebrate 75 years of political relations between China and Switzerland. And now I'm just popping around with pop-ups, and I do a lot with tofu. Because tofu in Switzerland is more like this product, you know, you can eat it, but if you not must, you better don't, or you don't want, or you just don't know. And if you don't know, you better don't. And I mean, it's fine, but you are missing out because, to be honest, I grew up with tofu. It's part of my childhood. It's part of my life. It should get part of your life as well. It will enrich you, I'm going to promise. But just shortly, in China, I was there. I probably ate more tofu than anything else because it's great and it's just super fun. And there's just some examples what you can do with tofu, which is not associated with like veganism or anything that is just like a plant-based protein resource. It's just, in China, it's just something, you mix it with meat, you mix it with everything. It's more like a vegetable, you know? It's just everywhere, and you can actually really, like, you find more tofu and meat in combination than tofu with vegetables, probably. But here we have like silky tofu, which we're going to do today. And silky tofu is a very traditional breakfast. It's sweet or savory. You can have it however you want. We all love it. And there we have a dish I made in collaboration with ETH as well. It's a dinner called Science and Cook. And I was there with Andrea Bach. She's a student from Patrick, and we did something with tofu. And then we have a tofu skin salad. I don't even find this in Switzerland. Somebody should make it and bring it. And then we have, of course, tofu skins, which it's like the bean curd. It's what we're going to actually side produce here as well. But just to give you a little euphoria about tofu, so we can deep into that now. Yeah, thank you.
Thank you so much, Michaela. So you said that we should integrate tofu more into our lives. So why not go for like bircher muesli with some tofu?
I would love it.
You would love it. Wonderful. You can convince me the next time we meet. All right. So, but to get started a little bit, I want you to think about, what did you have for dinner last night? So now I can see some people still nodding, thinking. I know it's a hard question because sometimes deciding for what you want to eat is always very, very difficult, right? But you know what? I'll make it very easy. I'll just ask Thomas.
Oh gosh, I wasn't prepared. Yes. So yes, well, actually I had a very special celebration. Actually it was with my family and the family of my wife. And we had a very traditional Zurich dish, so the Zurich Geschnetzeltes.
Oh, me.
With Rösti.
And you, Michaela?
So because I am testing a lot, I actually make a lot of dishes of the side product of the tofu making, okara, and I made a filling for dumplings. It's a okara dumpling. Yeah, I call it like that.
And how about you, Patrick?
Oh, you shouldn't have asked that question. So honestly, I was a bit tight on my schedule. I had to read some stuff. I had to do some stuff. So due to convenience, I just had some sourdough bread. I had some cheese, some apples, some cucumbers. So yeah, unfortunately, my dinner wasn't as complete as yours. But as you can see from the answers that we got just from us, right? Food is a really personal choice. So it's you that decides, what should I eat today? The thing is, though, even though it is a personal choice, it has a global impact on everybody. Because if you now think, okay, so you decided Zürcher Geschnetzeltes, okara, if we sum it up over all the people now in this room, the global impact is actually quite big. Because obviously, when we consume something, we use land, right? We use water, we emit greenhouse gases, but most importantly, it affects also our health, and it causes also labor on the field. So all of these aspects matter when you produce something, when you eat something. So the next time you think about what you're eating, I mean, you should always take this into account. But of course, I'm not here to tell you what you should be eating, because I'm a food process engineer, so I will not give you dietary advice. But the good thing is I have other people that have done this for me. So, for example, you can find the EAT Planetary Guidelines. So the nice thing about the EAT Planetary Guidelines is that they take into account not only nutritional quality, but also quantity. So meaning how much of a food should you technically eat? Because usually people ask, is this healthy or not? And the usual answer you get from a scientist, it depends, right? It's really like how much, when, what other things do you eat? So nutrition is a really complex topic and a highly controversial topic. But if you follow these guidelines, you cannot actually go that wrong. So imagine half of your plate should be vegetables and fruits. As a family of 4, such as mine, this is a lot of fruit and vegetables, right? But most crucially, the amount of meat that we eat is quite high in Switzerland. It's about 3 times the recommended intake of meat. So what we should do, we should increase vegetables. It makes sense. I think your grandmother and your mom, your dad, they probably all said the same thing, eat your veggies, right? So this explains, it says the same thing, eat your veggies. But how do I make sure that I do not eat so much meat, right? What else can I eat if I don't eat meat? So you go in the field and you can find different raw materials that can provide you proteins. So for example, the most prominent ones are legumes. Legumes have a variety of nutrients. Cereals have a little bit less proteins, but some of them have some higher quantities, and nuts and seeds. Now, if you just consume these, it's nice, you can make a stew, you can make a dal, you can combine these, but somehow you need to get more out of it, right? You want to do something exciting, you want to cook with it, you want to create something nice with it. So you should process them or cook them into a nutritional product. So plant-based alternatives can help you diminish your meat consumption because you can stick to normal traditions. But what if I tell you that plant-based products have always been part of our tradition in some countries? So tempeh is around 300 years old, tofu around 2,000 years old. So plant-based alternatives have been existing and they are processed, produced by using these raw materials. And of course, nowadays you can find even more exciting products produced by these raw materials. So you can find cheese using fermentation, lupins and cashews as a basis, or I had to show, of course, planted, right? So a steak, for example, made by soybeans and rice, or you can have plant-based eggs. That's kind of like the silken tofu as well. You can also make this with tofu, and you can find milk. So nowadays you have lots of variety, and there are options if you want to diminish your meat consumption. And the nice side effect that you get from eating legumes and cereals and nuts is that you do not only have the protein, you have all of the other stuff, and that's what people sometimes forget. If you eat legumes, you also get all of the good fibers in there, which is good for your gut health. So next time you think about, what should I eat tonight? Think about me or us, and then we can talk next time. So let's start with the soybean. So out of all legumes, the most prominent one is soybean, because I can imagine all of you have heard before of a soybean, right? This is a field of soybeans, and this is the soybean. So the nice thing about the soybean is that it can fix nitrogen, so you don't need lots of artificial, well, not necessarily artificial, but you don't need to use lots of fertilizers, right? The good thing also about the soybean is that it has a diverse range of nutrients. You can find important fibers for your gut health. You have a complete set of proteins. You have micronutrients, very prominently iron, although it's non-heme iron, but still it has a high iron content, but that's why we need to process it. And we have unsaturated fats inside. So soy is actually quite a nice legume to work with, because as we will see tonight, there's lots of variety of dishes that we can do. So as I said before, one thing is you cannot just eat a soybean. If you eat a raw soybean, it will cause severe indigestion. I don't know if you ever had these cases of bean legume intoxication. It's really not that nice. So you need to cook a legume, you need to degrade the anti-nutrients, and you want to eat something fun. Cooking is always cooking and eating is always something fun, so you should process it and cook it into something. So there are a variety of things that you can do. You can create soy milk. We will do that tonight. Oil soy flour. If you ferment, you get tempeh and soy sauce. If you use the green, non-ripe soybean, you get edamame, tofu. If you use an extruder, you get TVP. So there are lots of different things that you can make out of the soybean.
Oh, now it's where you get the equations. That's where it gets bad. So be ready. So actually, we wanted also to kind of bring in a little bit of the biophysics side. And now we are talking about these amazing products, particular tofu. And one aspect is, of course, the mouthfeel and the texture. And so if we have to think from a biophysics perspective, how can we picture this idea of texture and mouthfeel? So a really nice way to start is to think about elasticity. So we are talking about the spring, which is the workhorse of any physicist. And so the way in which we would think about the elastic properties of our tofu is to model the tofu as this cylindrical material of length L. And then we can test the material's property by applying a force onto this piece of tofu. And so this introduces a very fundamental concept in mechanics, elasticity, which is the stress. Perfect. So the people that are new, we clap every time we see an equation. So there will be more, so please be ready. And so what this is telling you is the stress is the force applied per unit area A. Now, as a result of this applied stress, then the material deforms by a certain amount, which is delta L, and this introduces the next equation, which is the strain. Which is the ratio, effectively the deformation, the relative deformation, so the delta L with respect to the original length of the material. And now the two quantities are related together. And the key equation here is the Hooke's law, which tells you, as you can see here, it relates the stress to the strain. So for an applied stress, we get a resulting strain, so a resulting deformation. And the proportionality constant is this factor E here, which is called the elastic modulus. And what is very important to remember is that this elastic modulus is a materials property. So it really depends on the material that you are probing and really on the structure of this material. And so if we were to plot this relationship in a graph where you have the stress versus the resulting strain, we would have a curve like this, where the slope of this line is actually the elastic modulus. Now, of course, this can vary from material to material, so you can have something like this or something like this, which would be a little bit softer. So this would be, for example, a harder type of tofu, so for example, firm tofu, and here a softer type of tofu, which would show a lower elastic modulus. So for an applied stress, you would get a higher strain, so a higher deformation. Now, as I said, the elastic modulus is very important because it's a materials property. And so it allows us to characterize, for example, tofu or looking at different ways to play with tofu and how that changes the elastic modulus. So one question is, what are the units, the physical units of this elastic modulus? And so if you look at the equation, sigma has units of pressure, so it's a force per unit area, and the strain has no units because it's a dimensionless quantity. And so from this equation, you see that E has to have the same units as sigma, and so it also has units of pressure. Now, pressure is a force per unit area, and we can rewrite this as an energy per unit volume, because a force times a length gives you an energy. And this is very interesting, it's very profound, because what does this tell us? It tells us actually that the elastic modulus somehow measures the amount of energy that is stored in the material. It's how much energy is stored in the material per unit volume. So it's like a form of energy density in the material. And so this leads us to the next equation, which, as you can see here, so is this elastic modulus tells you the density of bonds that we have in the material. So U is the characteristic energy of the bonds, and L here is the characteristic size or the characteristic length scale of these bonds here. Now, of course, this depends on the material and it can vary a lot, but this is really what the elastic modulus is measuring. It's measuring somehow how many bonds we have per unit volume in our material, fundamentally. And this is what we can change by processing, by cooking in different ways. We can change how we bond the different molecules, how tightly or loosely we do that, and how close they are going to be. And so if we look actually at how a tofu would look like, we can picture it like this, where we have the constituent molecules, which in this case are proteins, starch, fats, and so on. And these proteins bind together and they form like a protein network, and the starch is also bind together and they form a gel. And this is really what gives rise to the elasticity in tofu. And so I don't know if you've ever seen tofu under the microscope, but Patrick, can you show us how it would look like?
I know exactly now you wanted these slides and that I got all of the pictures. Now I know why. Yeah, so the nice thing, right, if you have a nice microscope or access to a nice confocal microscope, what you can do is you can look at structures under the microscope by using fluorescent dyes on different molecules, different aspects that you find. Here we have an example of something very similar. And what we colored here in red is the protein network and the cell walls. So if you look really closely, you can maybe see some debris of cell walls, because initially these are all plant cells, right? So you can find some debris in between. But more importantly, you can see that the red network is interconnected, meaning that it forms a nice gel. And the green are the starch molecules, the polysaccharides, which are, you can see these fun little round shapes everywhere, which are embedded inside of this protein network. And yeah, it looks just really nice. And thanks to my students that get to look at this every day. So in summary, we now saw, okay, so tofu has good nutritional properties, and from a science perspective, very interesting network properties. But I think, now we were talking equations and everything. I think we should now start with the cooking process.
Yeah, exactly. So we're going to make tofu from scratch, isn't it?
Yes, we shall get going. So I'm all sure you want to do this at home, so quickly take a picture.
But the recipe will also be uploaded on the website, so don't worry.
And it's not a secret. You can also Google it. So we soaked the soybeans overnight, like 12 hours. You can do 5, but I would like at least 5, but 12 is perfect. More is also good. But why?
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 Well, so what happens in the soaking? Well, that was a little bit unexpected, so we didn't practice it like this.
So first, we start with the soybean, right? And soybean is made out of plant cells. So schematically, we have a plant cell with the proteins, the starches, the polysaccharides, fats, and everything inside. And you said soaking, right? So with soaking, what we do is that the cells are hydrated with water. So water penetrates into the cell wall. It kind of starts softening up the cell wall. It kind of breaks a little bit up the cell wall. And the components inside also get kind of swollen and hydrated due to the water, because these were dried chickpeas, right? Dried soybeans that you used.
Dried soybeans, yes.
Dried soybeans. Okay. Well, and now?
And now? So now we're going to blend the soybeans. So this is not 250 grams of soaked soybeans, as you already figured. I, of course, prepared some in advance. And then we add the water. And depending on how good your blender is, you can use any brand of your trust. I have here NutriBullet. So we're blending around 30 seconds, as we all saw. That was 30 seconds. And
so you said about the brand, so how important to use a good blender as opposed to a not good one? Maybe we can ask Patrick, what is happening now in the blender?
Yeah, so in a blender, what you essentially do, you had the cell walls. Now you're breaking up the cell walls, and the better you blend it, the longer you blend it, the more all of the cell walls are broken up and the components are released into the liquid. So the proteins and the starch, they're freely hydrated, and it also improves the subsequent cooking process, because if you have them all in solution, the reaction will happen much faster, cooking reaction.
Exactly, so I go a little bit longer. Because it would be weird if it is not working here. So now we're going to filtrate it, and I have tested multiple versions. No, there are only two. So you can filtrate before or after cooking, but what I figured is if I cook the pulp with the water, the soybean soaks up all the liquid, and when I filtrate like this, I will not have a lot of liquid out of it. So I figured, let's do this way around. And yeah, it works fabulous, I have to say.
But Michaela, I mean, honestly, sometimes I'm a bit lazy. I don't want to, do the soaking part and everything. Is then something else that I could do?
You could buy tofu.
Before that?
You could... No, actually you can buy soy milk, but you have to be really, really careful about what brand you would buy. Or like there is in the Asia store, sometimes you have a soy milk that is from the tofu producer, and it's even called soya cream or something. It's not soya milk. And because I tried to do the shortcut as well. But then I tried all the brands of more like bigger brands who also use a lot of like additives to make them last longer. And actually it didn't work, because I think the bricks content, which I found out at some point as well, is very important.
We will talk about the bricks later. Don't worry if you don't know it.
It just didn't work with the coagulating. Yeah. So you can take a shortcut, but be very specific about it.
And so you mentioned, Patrick, the soy milk. So how is this related? So what is happening in this filtering process?
So in the filtering process, this is important because you have some components that will give you a gritty tofu, so you have to remove them. So all of the insoluble components are removed by the filtration, and all of the rest, all of the soluble components, such as the fats, the starches, and the proteins which were solubilized, they stay in solution and they essentially form the soy milk.
Yes, and so this is very important because now you mentioned these bricks, and this is actually a quantity that perhaps many of you don't know, but it's very important. And actually, we will measure the bricks later of the milk. But so, what is this? So this is perhaps familiar to some of you if you are into wine, for example, because it's a quantity that is used to measure the sugar content of, for example, wine, but also honey, for example. And so it is defined effectively as the weight percentage of sugar in a solution. So it would be, for example, how many grams of sugar you have per 100 grams of your solution. And the symbol is this degree of bricks. And now, how do we measure this? So we have here, and we will use it later, a refractometer, which is the instrument that everybody should have at home. Actually, this is a really fancy one, but you can buy a 20-euro version of it, also online. So it's actually not that expensive. So for example, for Christmas, you can buy a refractometer to make your tofu. And so how does it work? So this is really a very interesting topic because it actually touches on a quite interesting physics concept, which is the concept of refraction. And so the concept of refraction is the idea that when light goes, for example, through water, it changes direction. And this is the reason, for example, why when you put a spoon into a cup of water, it looks bent. It's really because the light is refracted. So this is the process called refraction. And this is the principle that underlies, for example, how a glass prism separates light, because the way in which light is refracted depends also on the wavelength of light. And so in this way, then the prism can separate white light into its colored components. And now, how are we using this? Well, as I said, the idea is that when light goes through another medium, for example, a solution, it changes direction. So if we have an incident light, some of it is going to be reflected, but some of it is going to be refracted, and it changes the angle here. And this is describing the change of direction. And so this is called the refraction angle. And now this refraction angle can tell us about the properties of the solution through our next equation, which is Snell's law, which tells you effectively that the ratio of the angles of the incident light and the refracted light is related to the ratio of the refractive indices of the two media. So in this case, it would be air and our solution. And now the point is that these refractive indices have been measured and tabulated for a number of substances. And so we know exactly how to go from this measured refractive index to the properties of the solution. And this is effectively what the refractometer does. It measures these refractive indices and then it converts this into the bricks. And so, for example, if you have and this is for the classical case of a sugar solution, where you have increasing concentrations of sugar that changes the refractive index in a particular manner, and so the machine is able to tell you what percentage of sugar you have. Now, of course, if you paid attention, you probably realize that actually in the soy milk, there is not only sugar, but there are a lot more things. There are proteins, for example, and they are also going to contribute to the bricks. And so even though the bricks really comes from the idea that it's a weight percentage of sugar, actually when we measure the bricks here, it's going to be a combination of components, including sugar, but also of the proteins. And so when measuring bricks, we are kind of measuring how much material we have in our milk. And this is very important, as we will see, for forming the gel, for forming the tofu. And Michaela told us that actually there is an ideal range of the bricks for making tofu. It should be between 8 and 12. And so, Patrick, can you show us a little bit how this instrument works?
Sure. It's, 8 and 12, technically, that would be really sweet, right? If it's only sugar. So it kind of indicates you when you taste it that for sure there's more than sugar inside, because it's all of the proteins interfering with the light. So it usually works on the first time. So we're going to try it out.
It did work before, beautifully. So let's see. We will just add a couple of drops here. And it's very simple because it's a nice household device. Yeah. And we can see, can you see it? Yes, you see 8.4. It means we can make a wonderful tofu.
We can make one. I'm glad.
Yeah. Now, I should really clean this because I borrowed it from my group. And they will never borrow anything again if I don't clean it. I need to make sure.
Okay, perfect. So now that we have our bricks, you cannot do tofu without the bricks. So what is the next step?
So, cooking. You actually measure the bricks after cooking, but let's just ignore this. We're going to cook after very fast going through the filtration process. We're going to cook this wonderful soy milk now for about 8 minutes. Of course, I cooked it before a little bit, so we don't have to wait forever.
Does it have to come to boil, or should it be at low heat?
It should boil once, and then it has to go over the sides of the pan.
Like it happened before,
like
yes?
It happened before. So you lose a little bit more water. No, don't do it. But you should be very careful so the bottom is not burning, because if it burns, it doesn't taste that good. I also tried this, really not. And then after it boiled once, it will. You can just boil it at like medium temperature, 8 minutes, not less. More is okay.
boiling over would be a good topic for next time.
Okay.
Perfect.
That we can talk about.
And so what is happening during the cooking process?
So during the cooking process, we have these proteins inside, right? And now the proteins are outside of the cell membrane. It means that these proteins can move and they can interact and they can, in this case, they will denature and they will unfold. What also happens, starch will gelatinize, so it will thicken after cooking, and we will form a stable emulsion, because in soy, what people often forget is that it has actually also a good fat content. So these oil droplets are stabilized, forming a stable emulsion inside of the liquid. And if we look at this closely under the microscope, before cooking, the proteins are barely visible because they're solubilized in solution. You can barely see them, but the starch granules are big and you can see them present here. So as I just mentioned, the starch will gel, the protein will start to unfold and aggregate, and most importantly, the anti-nutrients are degraded. If you don't do the cooking step, it might lead to some digestive problems, let's say it like this.
Great. We don't want that. Okay, so this is almost cooking. We're almost there. Let's see the temperature. So
what temperature do you want?
So we want it boiling, and then it should drop until 80 degrees. We now have 85. That's perfect, because then I have like time. That's good. We want time, because if I drop it on here, and now if you see the pan, it's very, very dangerous. We were almost there. Oh my God. So we're going to the coagulants. So we have to actually coagulate the soy milk, so we get tofu. And the most classic way, and on the most tofus you buy in any store, you find it with nigari. But we are using today glucose delta lactone and gypsum. And it is done like you take some warm water. If it's cold, it will build lumps, right? We have tried this as well.
So I hope it comes back.
Gives me time to do
Yes,
whatever
exactly.
I want here, right? It's very important. One bowl has to be kind of Asian.
Yeah, that makes the whole difference.
The other one is more ticinese, Phil, oh, this is not really done. Great. There is no lump. There was one, but we ignore it. So I have this soy milk now. It will be down on 84.5. Okay, that's maybe too much. This is my technique my mom always taught me when the tea was too hot. I'm going to pour it in between 2 cups and it's going to be great. Does it happen, or is it only like Chinese mothers doing this? I don't know. Or Moroccan, maybe. I don't know. Let's see again. Perfect. 82. Only 2 times more. Great. Good. And now I'm pouring it from a little bit higher. You don't want to stir it afterwards, because then you're going to like interrupt the coagulation process. What a word. You spill it a little bit on the side. It's always good. Not going to risk more. Good. And then you cover it both. Gypsum can stay here. And glucose delta lactone can go into steam for 20 minutes. About on 80 degrees. And yeah, what's happening with the coagulant?
Now comes the exciting part, the gel network formation of proteins. So by either adding something that will release H+ ions, so an acid, will help form a protein network, or by using salts, we can also form a protein network. So what is this like a protein network, right? If you think about in very simple terms, what you form is you form bonds between the proteins, but you leave space in between, meaning that you have space for the water molecules to stay inside, so you form a nice gel.
And that's where the formula comes in, the U divided by L cubed.
Exactly. So depending on what we add, we get a different tofu. So if you add an acid, you will rather get a softer tofu. But if you add the salt, you will get a really firm tofu by aggregating the proteins. And we usually look at the proteins in a very simplistic way as a sphere. But as we will see later, they are not just a sphere, and they are covered with charges. So what exactly is a protein, right? So this is a very simplistic model, just talking as if it's a round sphere inside of a solution, very simplistic. But in reality, and the protein that you can find inside of the soy milk, the molecular structure looks something like this. You can see that it's a long line. It's like at Europa Park. It's one of those crazy ways which goes around in every type of direction. And this is due to the chemical formula which causes the protein to take different conformations. And the protein is made out of the different amino acids, and the amino acids are formed in a long chain. And this long chain at the end determines what the protein structure looks like and where the charges are, because as we will learn later, the charges also depend on the type of amino acid that is present at the defined location.
Yes, and these charges are very important. First of all, because they gets us back to the biophysics side, but on the other side, because really they play an important role in the gelation process. And so as we have seen, there are two ways in which we can actually activate this gelation process. One way is by using the acid, and one way is by using the salt. So let's start with the acid. So what is happening there? So of course, when we're talking about acid, we all think about pH. And so here comes our next equation. And so the equation here tells you that the pH is actually related to the concentration of hydrogen ions, so these H+ ions, which is what actually contributes to the pH. And then you know typically that this pH ranges between 0 and 14, with 7 being neutral and less than 7 is acidic, and then above 7 it's a basic solution. Now, what is an acid? Now, as I said, pH relates to the concentration of these hydrogen ions. And so an acid is actually a compound that is able to release these hydrogen ions. And so in a very simplistic way, we can think of an acid as a molecule of this type, which has this generic structure, which then dissociates into an A- and then our beautiful H+ here, which in higher concentrations is going to change the pH. And so as these hydrogen ions are released, the pH is going to go down and create a more acidic solution. Now, why is this very important? Well, it's very important in the context of proteins because it plays a role in determining the charge of the protein. And so in general, proteins have different charge depending on the pH. And so here is a very schematic way of thinking about it. In reality, it's much more complex. And also what this is showing you is that there is one particular value of the pH which is very special. And this has a particular name. It's called the isoelectric point. And it's a point at which the charge of the protein is 0. So it's the value of the pH at which the net charge of the protein is 0. This comes from actually the ancient Greek, isos, which means same. And this is very important because as we are adding an acid, we are changing the charge of the protein. And what we want to achieve is we want to change the pH in such a way that we reach this isoelectric point. And if the proteins have the charge, they are going to repel each other and to electrostatic repulsion. But if the net charge becomes 0, now they are able to come together and form these bonds and form this network that, as we have seen, contributes to the elasticity of the tofu. And so how does it work in practice here? So what is the acid in our case?
So the acid that we used here is gluconodeltalactone. And the special thing about this acid is that it slowly releases an H plus over time. And if we cook, we actually accelerate this process. And that's why cooking this releases more H plus ions. It means that we can create a firmer network more quickly. By the way, where did you get gluconodeltalactone? I mean...
Well, so you can order it online, in other countries, but Switzerland. So I think it gets used for Wienerli production as well. And gypsum I actually brought from China because there it's very easy to get, and I didn't find it. Every time I wanted to order it, it was like gips. You can, gips. And I was like, well, maybe that's not the right one. Yeah.
Okay.
Yeah.
So essentially, if we add this into the solution, what will happen? The proteins will lose the charge. So we usually say that before they have a colloidal character, it means that they can stay in solution, and due to the charges, they will not aggregate and form a network. So by adding the acid, we disrupt this mechanism, and the colloids will not be stable anymore. They will connect and form a network, and that's why we use the acid. You can also use other things, right? Like, for example, lemon juice. Have you used lemon juice before?
I have not, but it works too fast, in my opinion.
Yeah.
But you can try, I mean.
The thing is, if you add a really fast working acid or something very acidic, then this reaction will happen much faster, and then you get something which doesn't resemble a tofu, maybe more a polenta from Ticino or something like this. So it will be really grainy because the reaction will happen immediately instead of over time. Like this, we have a nice settling of the gel network, much more stable. Or maybe even vinegar, but even vinegar is just too fast. The acid is too strong.
But nigari you can get very much anywhere in Switzerland, online. Sorry.
Wonderful. And so, as we've seen, acid is one way in which we can control the aggregation mechanism, and another way is to add the salt. So how does the salt work? So actually, what is the salt? So perhaps you don't think about it. I mean, we all have table salt, for example, at home, but we don't think maybe what is it from a chemical perspective. And so actually, a salt is in general a compound that consists of positively and negatively charged ions, such that the whole molecule has zero net charge. And the example is really table salt, which probably many of you would know. It's sodium chloride. So the sodium is the positive charged ion, and the chloride here is the negatively charged ion. And so if we were to schematically, simplistically represent how a salt solution would look like, is we would have all of these positive and negative charged ions floating around in equal numbers, such that the whole solution is electroneutral. Now, of course, what is the salt in this case? Well, we have the gypsum, which is, in this case, a little bit more of a complex salt. It's actually calcium sulfate. So here, the positive ion is actually the calcium, which has now two positive charges, and then the negative ion is the sulfate here, which also has two negative charges, so they all neutralize. Now, what is the role of the salt? Now, we have to understand what happens if we now take a charged object, which is, for example, our protein, we put it in solution, and then we add salt. So how is the salt going to affect the charge of our protein, of our object? And so this brings us to a very fundamental concept, which is called charge screening, and in particular, the concept of the Debye length that, as I was discussing with my colleagues, is actually such an important concept to know if you're making tofu. I mean, you cannot make tofu without knowing about the Debye length, as you will see. So please pay attention. And so what is this Debye length? So imagine we have our negatively charged particle, which is our idealization of the protein. Now, we add the salt. Now, remember the salt has these positive ions and the negative ions. And now, because the protein or the particle is negatively charged, what will happen is that very close to this particle, the positive ions are going to be a bit more attracted. So you will form actually a layer just next to the particle where you have a higher concentration of the positive ions. And you will have a lower concentration of the negative ions, which will be there, and far away from the solution, from the particle, we will have an equal amount of negative and positive ions, such that we have an electroneutral solution. But what this means is that actually we are creating this layer around the protein or the charged particle, which is now consisting of a lot of these positive ions. These are called counter ions because they have the opposite charge as our particle. And what these ions are going to do is, because they have the opposite charge to our particle, they are going to screen the charge of our particle. So if we are actually sufficiently far away from this particle, away in this point here, because of the screening from all of these charges, we are actually going to see no charge from the protein. So it will appear as if the particle has no charge because of the screening. And this is a very fundamental phenomenon. That means that salt effectively screens the charge. And this is described by the Debye length. So it's called the Debye screening length, lambda d. It's given by this wonderful formula over here, which looks a little bit complicated. You see, it depends on the temperature T, on it. Here is the elementary charge here, and in particular on the ionic strength. So the ionic strength is practically, if you want, the salt concentration. And this Debye length is particularly relevant here because actually Peter Debye was a professor here at ETH. So he won the Nobel Prize in Chemistry in 1936. And so actually a really wonderful place to be here tonight and talk about this important concept. And so, as I said, this Debye length depends on the salt concentration. So you see, the higher the salt concentration, the smaller the Debye length is going to be, which means the stronger the screening effect is going to be. And so this is very important because if we are adding the salt, we screen the charge of our proteins, and this allows then the protein to come together and form our network. And so we see there are really two different ways in which we can, in some sense, achieve the same effect, but actually not, in the sense that we are, at the end of the day, going to form this aggregation network, this protein network, but through two different mechanisms. And that's also why the result is going to be very different, depending on whether we are using the acid or the salt to neutralize, if you want, the charge of our protein. And so this is, again, the Debye length as I described earlier. And so now let's go to the last step of the preparation of the tofu, which is the pressing.
Pressing, yes. You can leave out this step if you want to stay with the silky tofu, of course. So I made a silky tofu with gypsum this morning. It's very important to break it up a little bit with chopsticks. It's also important. And then I have here a very fancy tofu maker press, but you can also make it with a cloth and a sieve, and it will not be square, but that's okay. And then you kind of drop it in. And then, divide it a little bit, you cover it. And you put this lid on. And depending on how heavy, I don't have a weight. This is a great weight. And depending on how long you have it in this situation, it gets firmer or not firmer. And this one is actually for 24 hours with like a 200 grams weight. So it's quite soft, but it's super cool. Yeah. What's happening?
Yeah, so what we're essentially doing here, you can see it still down here. For the water is coming out. So with the pressure, we are pressing out the water with this process. And as we learned before from Thomas, once we remove the water from this protein mesh network, what essentially happens is that we're decreasing the distance of this network. So this network compacts. And as we learned earlier, the tofu is going to get firmer and firmer the more we press, because the more water we expel from the network, the tighter these connections are. And the more connection points you have, the higher the gel strength is going to be at the end of the process. So now we looked at this entire process through all of these different processing steps on how to make a tofu. And the way how we generally look at this is that we always have a process which is given by what we do with the material. This automatically changes the structure of something, and the structure has a direct impact on the properties. Now, this happens on several length scales. You have nanoscale, microscale, and mesoscale. So, for instance, and if we look at the cooking process and the proteins, the cooking changes the molecular structure of the protein. So the protein will probably unfold, it will denature, it will change. And due to this process, this unfolding of the process, it will change the property, and in this case, the functionality of the protein molecules. They will be able to function and form gels if you look at it at a nanoscale. Now, this nanoscale has a direct impact on the next scale, on the microscale, because all of these single proteins, they form the network, right? So depending on the process that we have, for example, if we look at the filtering part, right? The more protein we leave inside of our milk, the stronger the gel network will be at the end. So the property and the structure that will be formed will be much tighter. The gel network will be much stronger. So on a microscale, also different processing steps have an effect. And if we'd like to have the complete picture of everything, we look, of course, at the mesoscale, going through all of these processes. So in this case, on the mesoscale, we're doing the gelation process. Depending on if we use a salt or an acid, we get a different structure because the mechanism is slightly different. And due to the slightly different structure, we get a different property. And in this case, using an acid or using a salt will lead to either a firm tofu or a soft tofu. By the way, there's an equation.
Wonderful. And this is, I think, a really nice summary. So you see how the molecular structure of what we are processing actually determines the properties. So it's really important that we understand what is happening at the molecular level and how doing different steps in different ways and changing the cooking process really changes the structure and in turn also the properties of the tofu. And so here, this slide is really to give you just a little bit of a summary of how many different ways we have to actually link the properties or different types of properties with the molecular structure. And so we don't want to go into the details, it's just to show you we can play with the hardness, cohesiveness, elasticity, crispiness, and it all relates to this pyramid to really how we process the food and how we are changing the structure at the molecular level. And what we are going to do next, as the next cooking, we will actually create a dish with 4 different consistencies of tofu, all in the same dish. And therefore, we are actually going to focus only on 4 of these ones. 2 of them we've actually already covered. So the more viscous and creamy tofu, so this is silky tofu, and then a more elastic one, which we've pressed. But then we will also try to create a more chewy, meaty-like structure, and also we will create a kind of crunchy, crispy, almost cracker-like type of tofu we will all combine in the same dish. And so let's carry on with the cooking. And there will be actually some samples going on. So we'll actually have 2 types of tofu. One and the other one we are processed differently, and you will discover what they are. And so pay attention to the texture and how they feel and how they taste.
Great. So I actually did a silken tofu and I steamed it inside a bowl. You can also do this at home if you want. And then I will actually cut it a little bit so it soaks up the sauce better. And you can see jellified very well. Then you're going to get two kinds of tofu. Start with the one with the toothpick inside, because that's the one, that's the firm tofu, the one that is only pressed. And then the second one is the koya tofu. It's the tofu that I freezed in my normal home freezer for a very long time, like 1 week. It's not that long, but it took long to freeze. And yeah, we can explain why we...
This is a wonderful thing, because actually it's a technique I didn't know, but apparently it's very much used in Asia, right, to change the texture of tofu. So it really relies on freezing the tofu for a long time. And so, yeah, how does it work, Patrick?
Yeah, so essentially what we do is we use the natural formation of ice crystals, right? It sounds now very simple, you know, putting it in the freezer, but it's because it's exactly this. Right? So we use the fact that we have water inside of the product, and if we freeze the water, they will form ice crystals, and we use this ice crystal formation to create gaps inside of the system. So you might have encountered freezing with, different food products that you have at home. So you have a nice ice cream, for example, with very small ice crystals. But I'm sure some of you have already counted what happens when you freeze something that you weren't supposed to freeze. So for example, when you look at something very similar like a cucumber, right? It looks nice, you can really break it apart, it's crispy. The cell structure is completely intact. All of the water is inside, so everything looks nice, right? It looks good. And a cucumber has lots of water. But what happens if you put a cucumber into the freezer? There's no snap, it doesn't look really nice. So what happened here is that the ice crystals, they actually break the cellular structure. It means that all of the water comes out and the cucumber becomes completely soggy, right? So not a pleasure to eat. And these are the two different examples. Sometimes you want to have ice crystal formation. Sometimes you would like to have very small ice crystals forming. And sometimes you really don't want to have ice crystals forming. So in my fridge, when it's really full, this happens at the end of the fridge, actually, because if the cucumber touches the end of the fridge, it will start to freeze and it will slowly move to the front. So if you haven't detected the freezing happening in your fridge, then you will slowly see it with the cucumber becoming moist and destroyed in the process. Now, if we look at this now in the kori tofu. So we start with a normal tofu, and as we saw, the tofu has water inside, and we have the gel network, as we saw before. Once we freeze, we form the ice crystals. Now, it is important to use a freezer that you have at home, because the freezing is actually not that efficient in your home freezer. It means that your ice crystals over time will start to grow. You will create larger ice crystals, and the larger ice crystals would actually push all of the elements, all of the different proteins and polysaccharides into the part where no ice crystals are. So the reason being that the things that you have solubilized will desolubilize. They will be pushed aside by the ice crystals. Imagine it's like icebreaker is not the right analogy, but it's basically something pushing aside everything and concentrating it into the corners. So at the end, we have a porous network after thawing the tofu. So in this case, we get a really spongy-like and a more textured tofu, more pleasant to eat, in my opinion, because you now have these empty spaces inside of the tofu, which you can use for marinades, for example, for different types of aspects. Exactly. So since we have a lab, we can look at this, what happens under the microscope. So here's the network that you've seen before of something that is close to a tofu. And on this side here, you can see what happened after ice crystal formation. So the ice crystals pushed everything aside, meaning that you now have these concentrated green regions of protein, and you can see that they're kind of fiber-like, as if it's something that is kind of meaty, right? You can see these directed growth and the gaps in between. And the gaps in between is the space where the ice crystals were inside. So basically, you're really creating huge ice, ice blocks inside, which push apart everything. And due to this, you get a much nicer texture inside of your free-structured product.
And you can concentrate all the sauce and the delicious things in those pockets.
Exactly.
So, and now the last texture that we wanted to do, Michaela.
Yes, before we do the texture, we need to, of course, put some flavor. So I quickly drop some sauce. Or I actually drop.
So what sauce is this?
So this is a mixture between chili, soy sauce, and fermented rice vinegar, and some sugar. I really go deep into that, as you can see. And then I have pickled radish. We do that a lot in China. I hope you don't smell it. It sometimes smells like fart. I always open it when I have a need. No. I'm joking. This is a very big kitchen joke. And yeah, not many people from the kitchen are here. Okay. Good. And then I will top it with, of course, some herbs and stuff and just make it look nice so everybody will come to my next pop-up in December in Wipkringen. So, and then we come to the last structure. It is deep-fried tofu. And it's very crunchy, as you can see, and we can finish this with another texture. We wanted to fry here, but then somebody said, no, you cannot fry, deep fry in the Audimax, are you fucking crazy? And I was like, no, sometimes only. Yeah.
It's a bit too much. But we can deep fry it in theory, right? So think of it in the physics terms. So what is happening actually? We are trying to give it a crunchy texture. And the way we are doing this is by frying. And by frying, we are actually removing moisture. And so there is a very interesting transition, which is when, as we reduce actually the moisture content of our tofu, we can reach actually a transition point where we go from this rubbery state that we have seen before to actually a glassy state, which is this crispy state here. And this is actually very interesting because if we go back to our strain-stress relationship, so how, by applying the stress, we get a particular deformation, what it means that actually we are actually giving elasticity to our material, but actually at some point we actually get a fracture. And so the material really breaks into many pieces. And this is due to this transition here. Now, food scientists like to explain this in terms of the water activity. And so, Patrick, what is this water activity?
Yes. So the water activity, it kind of tells you how humid is kind of my food product. And it also defines a little bit what will happen if I leave the food product just standing outside. You might have wondered on some days that why do my crisps get soggy but my bread gets dry on the same, even though they're very close to each other. The point is the water activity of the food product that you have. So depending if you have something, for example, with a high water activity, it can probably dry out faster. But if you have something with a low water activity, meaning that it has barely any water bound to the food product, it can for sure get more water from the humidity in your household. Now, one typical thing that you could do, right? If you have, for example, a very dry bread and you have some jam and you combine them. So once you combine them and you leave them standing, you will find that your bread will get really soggy. So what can you do, right? Just like with packaging, you can just add a little bit of butter in between both. It creates a perfect barrier, so you don't have this issue that your wet stuff will influence the dry stuff. Just add something in between, like a kind of artificial packaging, that you can prevent this from happening.
And of course, it becomes also more delicious.
And it becomes
more
tasty.
The butter. Fantastic. And so now that brings us to our last recipe, which is actually a tofu cheesecake. And so this is actually really to show you how versatile this ingredient is. And so, Michaela, do you want to show us? Again, the recipe is going to be published on our website.
Yes, of course. So we're going to check on our tofu because we're going to need it. Let's see.
So this is the tofu you just made before and you steamed.
Exactly. So it's the one with GDL and I have one with gypsum. I think I'm going to use gypsum because it's 300 grams. Approx. So we are going to use a blender. And I have tried because I thought, do I really want to bring a blender again? I did it with a whisk and I tried to bake it and it looked very ugly and I had to put chocolate and yeah. And then I actually tried it with the blender and it came out just like this picture. Oh no, there's no picture, okay. And so we put some tofu. You can also buy it, you don't have to make it. But of course you will be more proud if you make it by yourself. And then I have a cream. This time it's a vegan cream because it kind of makes sense. Or it doesn't, but you can choose however you want. And I think the tofu is like acting like an egg. And it's actually very, very cool. Do you want to go into that?
Yeah, I mean, in this case, right, it works as an egg substitute. Normal egg proteins have a lot of functionality. That's why you, as a vegan, you're really struggling finding products which do not have egg. Soy is a wonderful example where you can use it as an egg substitute. And it also tells you shouldn't be really afraid of, that you add something that is kind of like an additive, because in this case, you saw what we used. It could exactly be this that is used in a cheesecake.
Exactly, and the last ingredients is sugar, salt, and cornstarch. I already pre-mixed it because I ran out of boxes. And then I have some lemon zest, and if you want and go fancy, you go with an orange zest as well. And then I have some lemon juice, and then you blend it. And then you have a little liquid, like end dough, and you're going to bake it at like 190 to 200 degrees for like 50 minutes. And then, if you are lucky,
you can have a sample.
It will look like this. You just have to make sure to fill up the mold very high because it will not rise because there is no egg inside, of course. And if you're unlucky, it will look like this. Because I kind of thought it would rise, and no, I didn't thought, but that was my only mold, and then it looked like this, and I was like, am I going to do it? And then I was like, I should do it again, we're at ETH. And then I still thought I bring it, so you can laugh, yeah. But I covered it with chocolate, so it doesn't look too awful. Yeah. It's also an equation. That's cool. To clap all. Yeah, so it's enough for 420 people. We just have to be very careful with cutting. No, that's why we brought the recipes. But
so you can make it at home and actually try out a little bit what we've learned. Try to be a little bit of a scientist at home. See how by changing the processing, for example, the sequence of steps that you are doing, how the product changes, and try to rationalize it with what we've learned. So thank you very much, Michaela. Thank you very much, Patrick. It has been amazing. I think we deserve... And before we leave, I would just like to announce our next event, which is going to be at the end of November. It's going to be about the soft matter of cocktails, which I think is a really fantastic topic. And it's going to be with a wonderful barista, Sarah, that is actually here in the audience tonight. And the registration opens on the 4th of November, so be fast to register. And at the end, as usual, I would like to ask you if you could fill out our exit form to give us your feedback, give us your suggestions for new topics. Follow us on Instagram. And I would like to thank our sponsors, the Swiss National Science Foundation, the Cogito Foundation, the Department of Biology, and also the World Food System Center for organizing such a wonderful day to which we could participate. And really, thank you very much for being here. And again, a round of applause for our guests.